Stanford University.
All right, so welcome to Lecture 6. This is going to be the first in 2 or 3 lectures on what we call parallel patterns. So these are sort of very high-level abstractions, ways to think about how to decompose your problem in a parallel manner that's not quite at the very low level that we've been worrying about lately of writing individual kernels. We're going to sort of climb our way out of the trenches and think of things at a very high and abstract level. So, I mean, like I said, we'd like to get out of the trenches, right? How difficult have writing these individual kernels, how difficult have they been, right, for your MPs? It's a very low-level style of programming. It sort of makes you think a lot about a lot of variables that you don't necessarily want to be juggling when all you want to do is, solve some sort of computational problem. So, for example, some of these variables are like, thinking about how to map individual CUDA threads to individual elements of work that you need to do in your parallel task. That's sort of a non-trivial thing to have to do, and it's not something that comes up a lot in serial programming. Things like grid launch configuration, right? We have to think about how many blocks we want to launch in our kernel launches. We have to think how big to make those blocks of threads, sorts of variables like these. Other things that we've had to have been thinking about is how to manage shared memory, right? These resources like shared memory and individual registers that are way down there on the individual streaming multiprocessors. It's a lot of low-level work when all we really want to do is to solve some sort of high-level computational problem. So basically, this is a lot of moving parts to think about. It's not necessarily what we're interested in thinking about, right? We'd rather focus on our problem at hand. So, I mean, just to illustrate the point, you can think of like CUDA Mad Libs, right? So take a kernel and then, add some question marks, right? We've got to ask ourselves, well, how many blocks of threads do I want to launch? That's a big question mark. How many threads per block do I want to launch, right? How much shared memory should each block get? And once you've answered those questions, then you have to write the kernel, right? And it's like, well, now what do? I have to think up some novel implementation for a CUDA kernel. When in fact what we'd rather do is just talk at a very high level about the problems that we actually want to solve. And that's where this idea of parallel patterns comes in. So in the next few lectures, what we're going to do is sort of make the argument that there's these patterns that show up quite a bit in parallel programming. And if we can sort of recognize those patterns and figure out how the problem we actually want to solve maps onto those patterns, then we don't necessarily have to think so much about writing the individual kernels and all the details that are involved in that. So I guess what we'd actually like to do is to specify at a high level what we want to solve and not how exactly we want to implement it. And so what this is going to allow us to do is, as I keep saying, it's going to let us worry about the problem, the specific problem at hand, say, the matrix I want to solve, the linear system I want to solve, the k-nearest neighbors problems I need to solve, not necessarily what individual CUDA kernels I need to write. And what this is going to allow us to do is to basically defer all those hard implementation questions and problems and decisions to some expert user that's going to implement those patterns for us. And at the end of the day, we're just going to have to sort of take those patterns off the shelf, compose them together, and what we'll be able to do is talk at a very high level about the problem we want to solve, but also be able to get very high performance just by taking those off-the-shelf patterns. So let's think of some common sort of parallel computing scenarios that we often find ourselves in when we're talking about data parallel problems. So for example, suppose you have a lot of parallel threads and and they're all sort of computing on some result, and they compute, say, one result per thread. But you'd like to take that large set of results and sort of reduce them or condense them down to one value. So for example, say we have a lot of threads, millions of threads, they all compute one integer. We might want to ask, well, what is the sum of all those integers? And we tend to call this type of thing a reduction, because what we're doing is taking a large set and then reducing it to a single value. So this comes up a lot. We can compute sums this way, we can compute products this way, we can find the maximum element of a large set this way. It's a very common problem, and it has a sort of recurring theme in parallel programming. Another common scenario we might find ourselves in is to say, well, we have a large, diverse set of elements, say a big array, and we'd like to somehow partition that array or reorganize that array into some sort of organization that's more convenient for us to process. So, for example, say we're modeling a football game, and we're sort of modeling all the fans in the stadium at the football game, and we sort of have either Berkeley fans or Stanford fans, and we'd like to reason about them in sort of individual partitions of that set. So one thing we might do is to take the large set and split it in such a way that we've got all the Berkeley fans together at one end of the array and all the Stanford fans together at the other end of the array. And this sort of thing is called a split. Another sort of scenario we might find ourselves in is that suppose we have a lot of parallel threads and they have to sort of produce an output per thread that's variable. So, for example, you might be in some sort of particle problem where each of your threads is sort of crunching on a particle, and it might sort of split itself into a variable number of particles. This is sort of an expand operation where we're sort of allocating per thread many elements. Just another common scenario that might show up. So just before we sort of talk about these higher level patterns, we've sort of already been talking about a sort of a micro or primordial CUDA pattern throughout the class, and that's this idea of blocking your problem into smaller problems and sort of dividing them and conquering that way. So, I mean, this is just this theme of taking our large set of data and sort of partitioning it into blocks that are of a good size to work with. For example, these blocks could be small enough to fit into shared memory in your kernel. You could allocate these different partitions to individual thread blocks and work on them this way. And this is just that, the animation I showed before, where we've got this large data set sitting up there in global memory. We sort of block it up into partitions and do processing individually inside each block in a shared memory space, and then finally upload our results back to shared memory. So this is basically this common building block, this blocking pattern that we're going to basically use to build the more higher level abstractions that we're going to talk about towards the end of the talk. So basically, all CUDA kernels are basically built this way, in this blocked and partitioned manner. It may not matter for the particular problem that you're interested in, but because the grid launch forces you to think about block sizes, you still have to sort of think about blocking, even if your individual problem doesn't really merit it. For example, not all kernels require shared memory, but all kernels do require registers. So this blocking and this allocation of resources problem is sort of present and has to be thought about in any sort of CUDA kernel. And as I was saying, the patterns that we're going to talk about in the second half of this lecture and sort of next time are basically all going to be built around this blocking idea. So let's talk about how to implement this reduction idea that I mentioned before. So basically, the idea here is we've got this big vector or big array, say in global memory, and we'd like to look at all the elements in that array and basically turn that into a single scalar result. And basically, the way you can implement this is sort of describing the problem with what's called an associative operator. So you can remember from algebra, associative operator means that the order that we apply the operations in doesn't really matter, which makes it very suitable for a parallel implementation. So you can think of some of the associative operators that you can think of would be plus. So find the sum of a big array, or product. Find the product of all the elements in this array, or things like min, max, right? Find the minimum element or the maximum element of a big array, and or the list goes on. And so on the CPU, in a sequential implementation of this, it's very simple, right? You almost don't have to think about it. You just write a for loop to, for example, add up all the elements in this big vector. But in the sort of parallel world, we have to think about it in a different way. And in the previous lectures, when we've been talking about atomic operations, sum has been our sort of straw man. We've been talking about how to implement sum with atomic operations, and we've showed you sort of naive approaches that just hammer on a single sum out in memory with atomic operations, or more hierarchical approaches that use shared memory. But what I'm going to basically argue is that those approaches aren't necessarily the best thing to do, and in fact, you can do it entirely in parallel without worrying about atomic operations at all. I'm going to show you how to do that in the next few slides, but conceptually, you can think of this as another hierarchical approach or a tree-based approach, but the tree is sort of just conceptual. We're not actually going to build a tree data structure, but that's sort of how you should be thinking about it in your mental model. So let's just look at the serial reduction, right? We're just going to say implement sum of some array, say data of size n, and maybe n is very large, maybe n is millions of elements. So you don't have to really think about this on the serial CPU, right? You just write a for loop and start accumulating to a result, and after n accumulations, you're done. You can return the result. So this might seem very serial, right? Because it seems like every iteration depends on the previous iteration, right? So it seems like some order is implied here. But what I argued before is that since sum is this associative operation, the order, in fact, doesn't matter at all, and we can get rid of that serial dependence between loop iterations. So this is sort of a diagrammatic model of sort of how we're going to approach this problem in parallel. So say, up at the top, we've got some long array. Say we've copied it into shared memory in our CUDA kernel. So what we're going to do is basically do a sort of leapfrogging on this array in parallel, making these partial sums until eventually, we have a result at the end. And we're going to do this in sort of a series of parallel steps. Okay. So in this first step, say each of these orange circles corresponds to a thread. What each of those threads is going to do is it's going to take its partial sum that it's accumulated so far, and it's going to look within its thread block at the old partial sum of some other neighbor in that thread block that's not active. So for example, if we say that the thread block size here is 16, in this first iteration, only 8 of those threads are actually going to be participating in the reduction. So 8 of those threads accumulate a partial result. And then we insert a barrier to wait for that result to happen. And then on the next iteration here, we've only got 4 threads to participate. And we do in basically a log n number of steps, we can get the reduction of an entire n-length array. In each step, we sort of have the number of threads that are going to participate. And this is sort of one data access pattern that you could do in this interleaved fashion. You can also do sort of a contiguous data access pattern where the threads that are active are sort of contiguous instead of interleaved. And the performance differences in each approach is going to depend on things like what's going on in shared memory or the memory that you're actually accessing. We're not going to really go into that today, but do know that the results are going to be basically the same, but the performance, there could be subtle performance implications depending on the access patterns to shared memory. So let's look at the CUDA kernel that actually implements this. So the idea of this kernel is that each block of threads is going to work on a partial sum of the entire large array that's sitting out there in global memory. And we're going to sort of compose the total result by launching more than one of these kernels. So this is where the sort of tree-based idea comes in. So basically what we're going to do to implement this kernel block sum, which is going to basically take in an input array, and then per block, it's going to output one partial sum to this results array. So basically what we're going to do is we're going to need a shared array, sdata, to basically, as I keep saying, bring in a blocked portion of the input array. And then the first thing each thread is going to do is simply going to look up into, input a unique element, store it out to the shared array, and then we're going to synchronize, just to make sure that our portion of the array is in shared memory, and then we can start accumulating on it. So the next thing we're going to do in sort of a block-wide parallel fashion is to start accumulating those partial results into shared memory. So we're going to do this in a for loop. And the number of loop iterations that we're going to perform is basically the logarithm of the size of the block, okay? And sort of this offset variable is going to control this sort of leapfrogging pattern that we're going to do, from this diagram. So the offset encodes which neighbor I'm going to read from. And then it's basically very simple. In each iteration, each thread is going to check if it needs to participate. And that's a very simple sort of comparison against this offset. And then we're just going to add the current partial sum that we have in shared memory to the partial sum of some neighbor from the last iteration. Okay? Then after that, we're just going to synchronize to make sure all the data is ready. And then finally, there's basically nothing left to do. Since we're outputting a single result per block, we only need to have basically the first thread in the block do that final write to the results array. And then note that since the result is per block, we're going to use the block index variable to index into the results to find out where we need to write. And that's basically all there is to a parallel sum in a CUDA kernel. But just as an aside, note that we had a barrier in our for loop. So I want you to think about this question here. So is this barrier, is this sync threads going to be divergent? And what I mean by that is, are there some threads in the block that are going to call this variable while there are other threads in the block that don't have to call that barrier? And you might wonder, why does that matter? This might show the point a little bit better. So say we write this, this kernel, do I halt? And we want to solve the halting problem, right? Does this kernel halt? Well, we don't know, right? It's sort of data dependent. So depending on what's in that data out in global memory, some of those threads are going to call the barrier, and some of those threads are not going to call the barrier, right? So this kernel is never going to halt. Basically what's going to happen is that your machine is going to hang, and you're going to have to reboot your machine. So don't be very careful about where you put your barriers. If they're in divergent code, you're going to not be able to have a kernel that's correct. So basically what I showed you in our kernel before was this blockwise parallel reduction, right? So that's going to output one partial sum per block, but that's not really what we want, right? We want the sum of the entire input array. So basically with that same kernel, we can just apply it again and get the results of the entire array, and it's very simple. So to do that, what we're going to do is to allocate ourselves some memory to serve as the array to hold those partial results. And we're going to need a partial result per block that we're going to launch in the first launch, plus an extra one for the final result. So we're going to allocate num blocks plus the final result for the second reduction. And then we just call the kernel that we wrote before twice, right? So we launch the number of blocks or the number of partial sums that we need to compute in the first kernel launch, and then we get each of those partial sums per block. But then we want to take all of those partial sums and reduce them to a single result, and that's just another call to block sum, except this time we're only going to launch one block, right? Because we can fit all of those partial sums into one block. And then at the end of the day, it's very simple. To get that result, we just do a mem copy, but we're careful to get that final result there at the end. So here's basically the caveats to this code I've just showed you. So what happens if there are too many partial sums that you can't fit them into the shared memory of the first kernel launch, right? So that's going to be a problem. And sort of the dual of that problem is, well, what happens if that temporary storage that we had to allocate with CUDA malloc is too big, right? If you give CUDA malloc basically a large number of things to allocate, it's going to be pretty slow. So we'd like to keep basically our temporary storage that we need to allocate as small as possible, and we'd also like to keep, you know, the size of that shared array as small as possible at the same time. And so, you know, there are simple ways to get around this. And basically, the idea here is that you want to give each thread more work to do in that first kernel launch, right? So sum is both associative and commutative, so it doesn't matter in what order we do those accumulates, right? We could tell each kernel, each CUDA thread in the first kernel launch to basically serially keep summing into a local result, and then finally at the end of the day do that block-wide reduction in order to fit everything into 2 kernel launches. And you know, I'll just leave this as an exercise to you all if you ever need to implement this. So you might wonder about the sort of the algorithmic complexity of a reduction like this. So as we argued before, it basically takes log of n parallel steps to sort of crunch on those partial results. And each step that we do is going to basically do half as much work as before, right? So half as many threads in each iteration is going to participate. So sort of the step complexity of the algorithm is log of n. But you might ask, well, what is the work complexity? What is the actual number of additions that this parallel reduction does? Is it less than what a serial algorithm would do? Is it more? Well, as it turns out, it's actually what we call work efficient. So the number of adds that this implementation is going to do is basically the same as the number of adds that a serial implementation is going to do, which is kind of nice. You're not sort of wasting your additions here just because you're doing it in parallel. And then you might ask, well, how long do we have to wait for this parallel reduction to execute? And you know, this is, as another result, it turns out that if you have, you know, p threads or p processors in parallel, you know, the time complexity or the clock time on the wall that you have to wait is order n, the size of the array, over the number of processors you have, plus this basically cost of this logarithmic reduction steps. And you know, you compare that to just O of n for a sequential reduction. So that's basically reduction in a nutshell. It's pretty easy. There's some tutorial code up on the website that you can play with. So here's another sort of parallel pattern that I mentioned at the beginning of the talk, so split. So say we've got 2 arrays, basically some values, you know, just some numbers sitting out somewhere. And then for each value, I'm going to associate basically a key or a flag with each value. So in this case, we've got true and false flags per value element. So, you know, 3's flag is true, 1's flag is false, you know, etc. So we've got some sort of a key value thing going on here. So say I've got that input, and I'd like to have a new array that's basically going to reorganize the input to take all the true elements and push them to the front of the array. And it's going to take all the false elements and push them to the back. So I've basically taken my input and split it into 2 partitions that are easier to work with, just because they're contiguous. And so this sort of operation shows up quite a lot. It shows up in, you know, sorting, building trees. This is basically a stream compaction algorithm. And it's something that you'll be investigating or exploring in the next machine problem. And sort of a related problem is, say, this compact pattern. So what do we do if we want to output a variable number of things per thread? So say we take that same array and we want to remove all of these elements that are labeled 0. This is very similar to the last pattern, the split pattern I showed you, except that these other elements here we don't really care about. We just ignore them. We just want to take you know, the non-zero elements and push them to the front of the array. And this sort of thing, you know, for example, shows up in collision detection, but you know, it's a very common pattern. But you know, in general, say you want to output a variable number of things per thread. So this is sort of like a malloc problem per thread. Each thread wants to allocate some number of elements. So you know, for example, in your particle binning machine problem, we basically took the approach of saying each bin is going to have a fixed number of particles in it. But that can be kind of wasteful, right? Because what if you have space at the end of the array that goes unused? In general, we like to allocate as little memory as possible, and this sort of thing lets you do this. So, for example, say we have some array that says, per CUDA thread, how many things we'd like to reserve space for. So, for example, thread 0 wants to reserve space for 2, for A and B, and 1 wants to reserve room for this C, but this third thread doesn't need any room. So what we can do is basically, as I said, binning is an example. But what this allows us to do is to sort of take those things that we wanted to allocate and store them in a very compact fashion without sort of wasting any space. So that would be sort of another approach to the particle binning problem, other than using atomics with a fixed output, a fixed maximum output per thread. So basically, for these three patterns, for split, compact, and expand, each thread has to answer this question of where do I write my output, right? So in this last slide, how did this first thread know it was safe to write to 0 and 1, and how did thread 1 know it was safe to write to 3, right? If they're in parallel, they don't know. It's not immediately obvious how they should know what to do. So this question is, where do I write? Where is it safe to write my output? And it totally depends on what the previous threads wanted to do, right? So, if it's safe for basically thread 1 to write here, only because thread 2 needed 2 elements. It wouldn't have been safe to write to here because that first thread needed to reserve space. So basically, all these algorithms depend on what my other neighbors in the parallel kernel want to do. And that might seem like a very serial or ordered problem, but in fact, I'm going to show you this sort of super pattern that's going to solve all these problems for us called scan, which we can implement in parallel. So parallel prefix sum, or it's often called scan, is basically going to solve this problem for us. And it basically is given an array, some array A of a bunch of elements, and then some binary associative operator, so like plus or maximum, right? It's basically going to tell us a partial sum for each thread of what everyone in the front part of the array wanted to do. So for example, if my operator is addition or plus, then my scan for this series is going to return this series. And the way to decode this is basically as follows. Each of these results is going to be the sum of everything, all the threads before it in that array. So if, for example, there's nothing before thread 0, so it's a 0. 0 plus 3 is 3. 3 plus 1 is 4. So it's basically a partial sum for the entire prefix before each thread. And so scan shows up quite a bit, and there's all these different kinds of applications. You can build very fast sorts with prefix sum. You can use prefix sum in string comparison or stream compaction. You can use it to build run length encoders, tree operations, histograms. It sort of solves this allocation problem. And this is all kind of interesting because in serial computing, scan is basically totally unnecessary or worthless. You don't need it at all because it basically encodes this serial order that's sort of implicit to serial computing. And to sort of just make my point, let's look at some code that would do a serial scan on the CPU. So here's our input array from the previous slides, and we're going to output some result array of the same length. And to do that, we're just going to serially, compute a partial sum in every loop iteration. So we've got sort of this running sum variable that we initialize to 0. In each iteration, we're just going to output that running sum to the result, and then add the new input to the running sum. So it's very, it's a simple thing. It almost seems like we're not actually doing anything, right, in the serial world. So let's take a look at what a preview for what a scan algorithm would look like in a CUDA kernel. So here's our input array from before. And for the sake of the discussion, assume that input array is in shared memory, because we're going to do a pattern on it, or that's going to look a lot like the reduction that we did from the previous example. So we're going to proceed in log n steps like before, okay? And basically in each step, a number of threads are going to participate like we did in the reduction example. So what each thread is going to do, it's going to take its current partial sum and then add it to the partial sum of a neighboring thread that was before it somewhere in the array. So what we do in this first step is basically every thread is going to participate except that very first thread, right? Because it's already got its result. It doesn't need to add anything to its result. But all those other threads are going to basically take their partial sum, add an offset, and then accumulate to the partial sum. And then we're just going to proceed in steps like this. And in each one of these iterations, some number of these threads are going to drop out towards the beginning because they've already got their result and they don't need to continue along. And finally we're going to iterate a log n number of times. Basically each thread is going to add some value that's an offset number of elements array to its own value, and we can actually do this in place. We don't need an extra buffer or an array to compute this sum, this partial sum. So what we end up with is what we call an inclusive scan result. So what inclusive means is that each one of these threads basically includes its own value that it began with in its partial sum. So for example, our input, our first thread's value is 3, so it includes 3 in the result. And sometimes you don't want to include that each thread's sum in its result in the prefix sum, so we would implement what we call an exclusive scan. And you can build an exclusive scan pretty easily from this inclusive scan algorithm that I just showed you, simply by doing a shift through shared memory. So what we're going to do is take that array that's already in shared memory and then shift all the elements one place to the right to make an exclusive result. And basically, we shift in a 0 at the beginning to simply initialize the array. And then that result that gets shifted out to the right there is often called a carry, which is basically the sum of the entire array. And what's actually kind of a nice result is that you can use this algorithm to compute both scan and a reduction in one pass. So let's look at some CUDA code that would implement a blockwise inclusive scan. It's going to look sort of similar to the reduction example. Like the reduction example, we're going to have this shared array that we're going to use to store our partial sums. We're going to start off just by having each thread load its element into the shared array and then synchronize to make sure that the data is ready. And then again, we're going to do sort of a logarithmic number of steps or iterations. And like before, each thread is going to check if it needs to participate in the iteration, and that just basically depends on its thread index compared to this offset variable. And so like before, we're going to sum into our partial sum, wait until the results are ready, basically write out the partial sum to the array, and then do another synchronize to make sure that the data is ready. And then basically we're done. But unlike the reduction example, in this case, every thread has its own result. So instead of one result per thread, we're going to output one result, instead of one result per block, we're going to output one result per thread. But what I want you to realize is that in this algorithm, the results that we just computed were local to each block. So what that means is that block 0's result was correct, but block 1, which came after block 0 in the array, basically doesn't take into account the results of the first block, right? Otherwise, we would want to add this 53 to each of these results down here. So there's another step involved here. Basically, we need to propagate the results from the previous blocks to the results of all the subsequent blocks in the algorithm. Basically, what this means is that we have to do a two-phase scan. In that first phase, what we're going to do is this per block scan and reduce in one pass, like I mentioned. And then in the second phase, like the reduction example, we're going to take those results from the first phase and then propagate them basically to all our per block partial sums. And then we do some sort of final update to propagate the data that we computed in phase 2 and turn it into an exclusive scan result. And sort of the reason I've left this sort of vague here is that you'll have to sort of implement this algorithm for MP3. And basically the details and the skeleton of the algorithm will be more fleshed out in the assignment. So just to sum up, we encounter these patterns like reduce, split, compact, scan, and quite a few others, quite a bit in parallel programming. And it's nice because they let us sort of reason about the problem that we want to solve at a much higher level than individual CUDA kernels that we have to write. And you can use these patterns to implement even higher level patterns and abstractions with them. And in particular, scan is a very fundamental pattern that's basically totally necessary in parallel computing, but not so necessary in the serial world. And David sort of left out the best performance advice from the last lecture, and that is to simply get someone smarter than you to implement your code for you, right? Because they're going to do it much faster than you can, but not until after MP3. You still have to, write your own code for the third programming assignment. So we've got full code examples for both reduce and scan on the website. They will probably come in handy for MP3, and it's okay to copy and paste from these. So check out, the sum reduction and the block scan, and I think we'll see you next time. I think what we'll do is sort of yield the rest of the time to questions for MP2, and if you don't have any questions, yeah, we'll just see you next time. What's that? Oh, go for it.
Just one other thing, I incorrectly told some people not to use the external keyword when they're doing.
For more, please visit us at stanford.edu.